Now we need to focus more on how light and matter interact with each other. I want to start by saying a little bit about this term spectrum I've mentioned. A spectrum is effectively a graph. It shows light intensity on the vertical axis and wavelength on the horizontal axis. We have one here. Sometimes you will also see a spectrum given as a bar of color, like the one just below the graph. Light and matter can interact with each other in four basic ways. First, matter can absorb light. When this happens, the light hits the matter and stops. The photon's energy is converted to some other form, like heat. Second, the matter can reflect the light. In this case, the light bounces off the matter and continues in a new direction. When you've got a very flat surface, the light may all bounce off in the same direction. A mirror is an example of this. However, most other surfaces also reflect light. They just do it in a wide range of directions. We often call this scattering. The third interaction is transmission. In this case, the light passes through the matter. The direction the light travels may change some, but otherwise the light keeps on going. A piece of glass transmits visible light. Finally, matter emits light. This means that the matter generates photons that weren't there before. In other words, the matter is glowing. This takes energy, so the matter loses whatever energy is emitted away. Most matter does more than one of these at a time. In fact, if you look over the entire electromagnetic spectrum, you'll find that most things can do all four. For example, a person absorbs and reflects visible light, with different amounts of absorption at different colors. But we also transmit X-rays. That's why an X-ray machine can see through us. Finally, we emit infrared light. We'll see why shortly. Now try applying the ways light and matter interact to this question. What would you see if you used a red flashlight in a dark room to read red writing on white paper? You should think about what happens to the light hitting the ink as well as the paper, and what you'll see with your eyes. Now that we've seen the basics of light and matter interaction, let's focus on the emission of light. There are many ways that light can be emitted, but I would like to start with one very important one: thermal radiation. This is also sometimes called blackbody radiation, but I'll stick with calling it thermal, since that's the term the textbook uses. The idea behind thermal radiation is simple. We know that light is an electromagnetic wave. In other words, a moving object with an electric charge should produce some sort of light. However, atoms are made of charged particles, protons and electrons. So how do we get atoms moving? Actually, atoms are always moving. We saw that back in Chapter 4, and again earlier in this chapter, when we pointed out that moving atoms are what define temperature. The faster the atoms move, the higher the temperature. So let's put these ideas together. Moving charged particles generate light. Matter is made of moving charged particles, with the motion depending on the temperature. Hence, any matter warmer than absolute zero emits light. That's what we call thermal radiation. If you heat up a piece of metal, you can see an example of this. As it starts getting hot enough to glow, you start to see a faint reddish color. As it gets hotter, it gets brighter, and the color moves toward orange or yellow. If you get the metal really hot, it would glow with an almost blinding white light, although most things would melt before getting quite that hot. What I just described for a hot piece of metal applies generally for thermal radiation. As an object heats up, the light it emits changes two ways. The brightness goes up rapidly, and the color changes towards shorter wavelengths. In other words, it gets bluer. Also, there are only two things that affect the spectrum produced: the temperature and the size of the object. We've talked about what temperature does. Changing the size just changes how much surface area it has to glow. So a bigger object will be brighter than a smaller one, but the colors produced are the same. Nothing else matters, including whatever the glowing object is made of. The only limitation is that it has to be opaque. In other words, you can't see through it. If you can see through it, then it produces an emission spectrum. We'll see those a little later on. Here are some thermal radiation spectra. Remember that a spectrum is a graph of brightness versus wavelength. Like the last one we saw, this spectrum covers a wide range of wavelengths, not just visible light. The visible spectrum is that small vertical strip marked with a rainbow. So, do you remember what's on either side of the visible spectrum? Take a moment, see if you remember, then click forward for the answers. Do you remember it? On the left side, we're beyond the violet part of the spectrum, so that must be ultraviolet. The right side is past the red part of the spectrum, so that's infrared. Now let's look at that red curve. It represents a star with a temperature of 3,000 Kelvin. Actually, it's the curve for a 3,000 Kelvin anything. It doesn't have to be a star. The curve shows the standard pattern for thermal radiation. It's shaped like a single big bump, spread out over a wide range of wavelengths. There's a single peak, the highest point on the curve. This represents the wavelength where most of the light is being emitted. In this case, the peak is in the infrared part of the spectrum, just a little to the right of the visible spectrum. So any object with a temperature of 3,000 kelvins emits mainly infrared light, though it does produce some visible as well. You can tell that because the curve cuts across the visible wavelengths. Since it's higher on the red end than on the blue end, it looks yellow-orange to our eyes. Now compare this to the yellow curve, the one for a 6,000 Kelvin star, like our Sun. This curve is higher at all wavelengths, telling us that the 6,000 Kelvin star is brighter at all wavelengths. Also, the peak has shifted. The highest part of this curve is right in the middle of the visible spectrum. That means that the largest part of the light produced here will be visible light. Since it's fairly level all of the way across the visible light rainbow, it's emitting about the same amount of red, blue, and everything in between. To our eyes, that will look like white light. Finally, have a look at the 15,000 Kelvin star. This star is brighter still at all wavelengths. However, notice that the peak has shifted over to still shorter wavelengths, so it's now well into the ultraviolet part of the spectrum. A star this hot produces huge amounts of UV light. Look at where the blue line crosses the visible spectrum. This time, the curve is higher on the blue end than the red, so more blue light is emitted than red light. To our eyes, this looks like a blue-white glow. So once again, that's the general pattern. As an object gets hotter, it gets brighter, and more of the light shifts to shorter wavelengths. Finally, there is one more curve on the graph, low down on the right side. That's for an object at 310 Kelvin, in other words, us. The curve is low because we're not very bright. At least, we don't emit very much light. Also, it's entirely in the infrared part of the spectrum. So we glow in the infrared. That's why things like infrared night scopes work. They're designed to detect the infrared light emitted by objects at our temperature. Now we're going to be a little more quantitative about thermal radiation. We can be very specific about the wavelength where the peak of the thermal radiation curve occurs. The formula that describes this is called Wien's law, and it lets us get a sense of what kind of light an object will emit. Here's the formula. Lambda max is the peak wavelength. It's a measure of how far to the right or left on the graph the peak occurs. T is the temperature. This must be given in Kelvin. The number on top is a constant. We will always use the same number here. Technically, the unit should probably be written out nanometers Kelvin, but for historical reasons, we usually leave the Kelvin out. This gives an answer in nanometers. Remember that a nanometer is a billionth of a meter. Visible light runs from 400 to 700 nanometers. While this form of the equation is useful for predicting what kind of light something will emit, in astronomy, we usually have the opposite problem. We know what kind of light an object is emitting, we can see it. What we don't know is what temperature it is. Using Wien's law, we can find the temperature. We simply solve the equation for temperature, giving this form. Notice that the constant hasn't changed. If you studied algebra, you should see if you can figure out the steps you use to get from the top equation to the bottom one. Now let's look at an example of how to use Wien's law. We'll consider the sun. Like most stars, the sun emits thermal radiation. Its peak wavelength, where it puts out the most light, is at 500 nanometers, right in the middle of the visible spectrum. So we write down the formula here. Then we plug the wavelength in for lambda. We don't have a unit conversion since the wavelength is already given in nanometers. When we solve it, we get a temperature of 5800 Kelvin. So that's how we measure the temperature of an object without actually going there. Just look at the thermal radiation it puts out and measure the peak wavelength. When we put that into Wien's law, we can find the temperature. Remember this table? You should be using it to help you keep track of the equations we use in this course. Fill in the Wien's law section of this table now. Keep it and update every time we use a new equation. You'll find this page useful doing homework and reviewing for exams. Depending on your section, you may be required to submit a copy of the completed version for credit. Now it's your turn to do one of these calculations. In this case, use Wien's law to calculate the temperature of the filament of a standard incandescent light bulb, the kind that's not very efficient. Remember to include the formula and show your work. When you're done with that, notice that peak wavelength is not in the visible part of the spectrum, the range from 400 to 700 nanometers. Can you tell what part of the spectrum it is in? Also, since the peak isn't visible, can you explain why we still see it glowing? Now that we've looked at thermal radiation, it's time to put that into a larger context by discussing different kinds of spectra. We usually divide spectra up into three main types: continuous, emission, and absorption. A continuous spectrum is one that goes through a series of colors with no gaps or jumps. Thermal radiation is the most common example of a continuous spectrum. Even though thermal radiation is emitted light, it doesn't produce what we call an emission spectrum. Emission spectra are produced when you heat up a thin, transparent gas. The light it produces isn't a continuous rainbow. Instead, it's made up of a discrete set of bright colors called emission lines. There may be just a few lines, or the spectrum may look like a barcode, depending on what gas is emitting the light. When we look at a glowing nebula in the night sky, we're often seeing an emission spectrum. An absorption spectrum is the opposite. Instead of bright lines on a dark background, it consists of dark lines on a bright background. Absorption lines are formed when a continuous spectrum, such as that from thermal radiation, passes through a thin gas. The gas absorbs light at very specific colors, producing the dark lines. An example of this happens when we look at the light from the sun. The sun's surface produces a thermal spectrum, but then the light passes through the sun's atmosphere, and later it passes through the Earth's atmosphere. Both of these produce absorption lines in the sun's spectrum when we observe it from Earth. Each chemical element and each compound has its own pattern of absorption and emission lines. This pattern is the same whether you're seeing it in emission or in absorption. These act as a sort of fingerprint, telling us which gases are present. So when we look at the spectrum of an object, one of the most important things we can learn is the object's composition. Have a look at this spectrum of the sun. It's been spread out incredibly long, so that they've had to split it up into dozens of smaller pieces just so that they could fit it onto a page. Each of the dark vertical bands is an absorption line. As I just mentioned, these lines are produced by the gases in the Sun's and the Earth's atmospheres. As you can see, there are hundreds of lines here produced by numerous chemical elements. We call the study of spectra this way spectroscopy. Spectroscopy was first introduced in the late 19th century, and ever since then it's been an incredibly important tool in astronomy. By allowing us to determine the chemical composition of objects in space, it has let us treat astronomical objects as more than just moving lights in the sky. Instead, these are real, physical objects that we can study just like material objects here on Earth. The modern science of astrophysics became possible from this. For example, back in the first chapter, we mentioned that Cecilia Payne-Gaposchkin was able to figure out what stars were made out of by studying their light. She did this by studying the spectra of stars. Finally, I should mention that it's not just gases that produce absorption spectra. Solids and liquids do too, but they're harder to interpret. That's because they usually don't absorb discrete wavelengths of light. Instead, they tend to absorb whole bands of color. This means that many closely related materials will have spectra that look almost identical. So while it's easy to distinguish broadly different materials like ice and rock, it's much harder to figure out exactly what kind of rock or ice you might be looking at.
Here's a table to fill in to remind yourself of the 4 major ways that light and matter interact. See if you can define each one without just relying on the name of the interaction. In other words, don't just say that reflection is when something reflects. Also, come up with some examples, but leave room so that you can add others as you learn about them later in the course.